So now we're going to talk about electric fields specifically. Now, an electric field is a region of space in which a charged object is going to experience a force. Electric field strength is the magnitude of the force experienced by a positive point charge due to its position in an electric field, right? And that positive point charge has to be a charge of 1 coulomb. So it's going to be the force experienced per coulomb of charge at that particular point in the field. And then the electric field direction is going to be the direction in which that positive point charge is actually going to be experiencing the force. All right, so we've got to know what the electric field looks like around point charges. So if we have a positive charge, the field is going to be going away from that charge in this circular radial way like this. And do note that when you have to draw these, make sure that you make the charge nice and big, right? And make sure that these field lines are leaving the charge at 90 degrees. Okay, so you don't want a field line that's going up like that off the side or something like this. That's a no-no, okay? And then if we have a negative charge, well, now the field lines are going to be going towards that negative charge. And notice here that what I've done is I've had the plus Q for one and the minus 2Q for the other. And what I'm trying to illustrate here is that when the magnitude of the charge is greater, the electric field strength is going to be stronger. And the way that we show a stronger electric field visually versus a weaker electric field is by using more field lines that are closer together. So on the right, we've actually got a stronger field than we do on the left there. Well, I think it's stage left. Anyway, okay. So then, in terms of field direction, remember, it's the direction in which a positive charge would experience a force, right? So that little white positive charge there would experience a force as that pink arrow shows, and that's then the electric field direction at that particular point. And same here, that little positive charge in the negative field is going to experience a force of attraction towards the charge, so that then is the direction of the field at that very point. Right. So when we have two charges in the same space, their fields are going to interact in order to give a net kind of field pattern. So we've got to be able to draw this, and this is what the field is going to look like between unlike charges. So I've got the positive and negative there, and notice that my field lines are still going away from the positive and towards the negative. And it's kind of like they're working together in between, right? So if you were to put your positive charge here, it would be pushed away by this charge, but it would be pulled towards that charge here. And that kind of shows us that you'll have a trajectory of that charge, if it were free to move, that's going to be similar to the field lines that we've drawn there. Right? And then if we have like charges, well, like charges repel, so they're not going to agree with each other, and the field around it is going to look something like this. And basically what this means is if you've got your buddy, the positive charge here, it's going to be repelled by this charge here, but it's also going to be repelled by the other charge. Right? And the two repulsions working together is basically going to cause it to push off up towards that direction there, as the field lines are going to indicate. Then for electric field strength, we've got two formulae that we need to be able to deal with. So the first one is this E equals F over Q, and that is the formula that we basically get from the definition of field strength, the force experienced per coulomb of charge, right? So in this formula, Q is the charge that is experiencing the force in the electric field. So I call this the at a point formula, because F is the force experienced by the charge at a point in the field, and Q is the magnitude of the charge at that point in the field. Right? And then the other formula is this E equals KQ over R squared, where Q is the charge that is creating the electric field. And I call this the blame formula because Q is to blame for the field being there. So that large Q is going to be the thing that's creating the field, that's to blame. And then the r squared is going to be the distance between the thing that's to blame and the point in the field where we're trying to find the electric field strength. Now, with multiple charge scenarios, like we've had with the Coulomb's law up until now, remember, the fields around the charge are going to overlap and interact with each other as we saw, and because these things are vectors, we can go and find the net field at any point just by adding up the individual vectors, that is the electric field due to the individual charges. Okay. So here's an example. The electric field strength at X is 84,375 newtons per coulomb towards the west. Okay, so where's X here? There's X, right? And west is this way, right? So we know that the E net at that point is the 84,375, and that's, I'm going to use left, but west. Okay. Although, I've got to be careful with left because I think it's going to be swapped. Okay, I'm going to use west. But then it might still be east. Okay, in that direction. Right. So, then A and B are 6 centimeters apart. What is the charge on B in nanocoulombs? Okay, right. So, we know A, right? So, this is very useful to us. So, I'm going to start with this idea that the net field has to be the vector sum of the two fields. So I'm going to say EA plus EB, right? Now I need a positive and a negative direction, and I'm assuming since the field is kind of ending up towards the left, I'm just going to use the direction of the net field as positive. So I'm going to take left as positive, I'm going to take right as negative for this field. So then the E net is the positive 84,375. And then the EA, we need to figure out what EA is, right? So let's do that separately. Okay, so the EA, we've got the thing that's creating the field, and we don't know the force or the charge of the thing at the point. So we're going to use the blame formula. So KQ over R squared. So we're going to have 9 times 10 to the 9 times 1 times 10 to the negative 9 divided by 0.04 squared. By now you know that the centimeters has to become meters. And so if we go 9 times 10 to the 9 times 1 times 10 to the negative 9, we'll divide that by the 0.09 squared, and I get here 1111,11,11 newtons per coulomb. Okay, and now it's crucial that we identify the correct direction. Now A is positively charged, and because A is positively charged, a positive point charge will experience a force A away from A. So the field at X due to A is actually going towards the right, which is our negative direction. All right, so I'm going to put here negative 1111,11. All right, so if I continue here, I can then go negative 1111,11 plus the EB. All right, and then we can find the electric field due to B only. So that's going to be the 84,375 plus the 1111,11, and that's going to be 85,486,11. Okay, and that again is newtons per coulomb. So now we're in luck because we've got the electric field strength due to B only, and we know that this EB is going to be equal to KQ over R squared, right? So this 85,486,11 is going to be equal to the 9 times 10 to the 9 times Q, which is what we're trying to find, and that's divided by R squared, which is 0.02 squared. Okay, so I'm going to take this 85,486.11, I'm going to multiply it by 0.02 squared, right? And then I'm going to divide it by the coefficient of Q, which is the 9 times 10 to the 9. And I get here that Q, right? So I'm going to actually just write QB, so you know I'm talking about B, is going to be 3.799, so 80, and then it's times 10 to the negative 9, but I know that we want the answer in nanocoulombs, and I know that times 10 to the negative 9 is nanocoulombs, so I'm just going to write here nanocoulombs and leave out the 10 to the negative 9. And then I've just got to decide, is B positive or negative? Well, I know that B had a field that was going into the positive direction, or the field at X due to B was going in the positive direction, which is going that way. So if a positive charge here is experiencing a force to the left due to B, then B must also be positive due to the repulsion. So the charge on B is then going to be positive 3,80 nanocoulombs. Fantastic, right? So now it's going to be your turn to pause and give this one a try. Fantastic. So well done if you did give that a try. Let's see how it went. So we've got two positive charges, A and B, and they're arranged as shown. We want to find the net electric field at point X, okay? And then we want to know what force would a positive 2 nanocoulomb charge experience if it were placed at X. Okay, so we're going to start and we're going to find the electric field at X due to A, right? So again, A is positive, so a positive charge at X would be repelled. So this would be a positive, a positive. That would be the direction of the field due to A, right? And then B is also positive, so a positive charge here would be repelled by B. So that's going to be the electric field direction due to B. Right, so I'm going to take this direction as being positive and this direction as being negative. Okay, so let's calculate this EA. So EA is going to be the 9 times 10 to the 9 times the Q, which is then 2 times 10 to the negative 9 all over the R squared, which is 0.03 squared. And then I know that A is going to be, let's see, times 2 times 10 to the negative 9 over 0.03 squared. I get here that it's going to be 20,000 newtons per coulomb. Okay, and note that electric field strength is often a number that numbers in the thousands. So don't be too surprised if you do get an answer like 20,000 newtons per coulomb. Right, and then the E for B, right, is going to be very similar, 9 times 10 to the 9 times 4 now, times 10 to the negative 9, and that's also 3 centimeters away. So this is still over 0.03 squared. Okay, so now I'm just going to go to what I've already got in my calculator and change the 2 to a 4. And when I do that, I now get an answer of 40,000 newtons per coulomb. Okay, and we're kind of not surprised that 40,000 is double 20,000, because if we relate the two fields to each other, we see that for B, we just doubled the charge, and we know that E is directly proportional to the charge that's creating the field. So if we doubled the charge, then at the same point 3 centimeters away, we're going to have double the field strength. Okay, so now my E net is going to be, now I said leftwards is positive, so that then is going to be the 40,000, right, which is in the positive direction, and then the EA is in the negative direction, so it's going to be minus 20,000, and that then is going to be 40,000 minus 20,000, and that's then 20,000 newtons per coulomb, and that then is in the positive direction, which for us is going to be towards the right, or towards the left, or west. I was going to say west. Okay, fantastic. So that's question 1. And then for question 2, what force would a positive 2 nanocoulomb charge experience if it were placed at X? Right, now here we've got to use our at a point formula because we're given the charge that is experiencing the force at X. Right, and fantastically, we know what the electric field is. So if we use this E equals F over Q, we now know that the net field is going to be 20,000, right? We know that the force is what we're trying to find, and we've got a positive 2 nanocoulomb charge, so this has to be 2 times 10 to the negative 9, which then gives us that F is going to be 20,000 times 2 times 10 to the negative 9, and I get that that's then 4 times 10 to the negative 5 newtons. Okay, but now again, we've got to talk about direction. Now, we know that the electric field direction is the direction in which a positive charge would experience a force. So because I had 20,000 to the west, a positive charge would experience a force to the west, and because this is a positive charge, I know that this force is then going to be going to the west. Okay, so well done for sticking through this presentation with me. I really hope you learned something. Remember, the best way to retain this information and really understand it is to do some practice. So make sure you get some past papers or you go through your notes and exercises, practice, 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 and then succeed. Thank you and goodbye.